Okay, thanks again, Christian. I hope you can all hear me well. So it's a great pleasure to give this last CHEMTalk talk of the year. So what I'm gonna tell you is the new updates on the work on the coherent magnetic properties of lanthanide coordination complexes. So let me see how. Yeah, so I mean, as I have said in previous talks, so basically what we do in my group is we make molecular materials, the coherent magnetic properties of which may form the basis for quantum technologies. So that's the general theme of the projects I'm going to talk about today. So, you know, you have probably by now, all of you heard these introductions about quantum technologies and qubits many times. So just here I will say that there is two important things that have to be achieved. So those are single qubit gates. So this is like operations on a single object. And then there is a coupled qubit operation. So this entangled gates. So entanglement and superposition are the two basic ingredients from which quantum algorithms they can be derived. So what we have done, we have actually started here you can see back in 2015 with some studies of incoherent dynamics. And since we have done quite a lot of stuff, you know, now we have some new papers from the PhD of Steen and Julius submitted, and I'm gonna update you about what is new. So in general, we work with the trensal systems. So those are these molecules you see up here. So there is a lanthanide center in the middle, and it is hepta coordinated. So 3 oxygens here in red and 4 nitrogens. And the important thing is that this is high symmetry. So it's in trigonal, local, and crystallographic symmetry, which makes things much easier when one wants to model things. And then you can see here, this is a typical single crystal we obtain for this system. So it's like a pencil shaped, and it has a size that is about 0.5 centimeter. So for molecular materials, this is quite large crystals. Maybe in other areas it is not, but for us it is. And well, it is big enough to be easily manipulated in the instruments we use. So this is very convenient. So these materials, they're also very stable. So these crystals that you can see here, I can leave them on the bench for a couple of years, and they're exactly the same after some years. So nothing happens to them. So they're very convenient for studies. Of course, now, you know, all the other advantages of molecular materials, they can be made in many copies, they can be functionalized, they're tunable, and so on. So I said we're working with the lanthanide complexes of trensals, but for the moment we haven't looked at all of them. Actually, we have just looked at 2 of them, gadolinium and ytterbium, but of course the rest, they are candidates for studies that we will perform in the coming period. So we started actually with ytterbium. So for those of you that can't really remember how the electronic structure of ytterbium is, so ytterbium has 1 hole in the 4f shell, so that makes that it has a orbital angular momentum of 3 and a spin half when they couple together to give you the total angular momentum. This can be 5½ or 7½, and because the shell is more than half full, you get the 2f7½ term to be the ground, and the excited one is at 10,000 wave numbers. And this is a wavelength that corresponds to the near infrared. So one can do optical spectroscopy, so emission and absorption. And when we combine all this with magnetization measurements and electron paramagnetic resonance measurements, we get those energy levels that you see here. And we can also determine the composition of the Kramer's eigenvectors, which is this one that you see here at the bottom of the page. And the important thing is that the ground Kramer's doublet, it has a component for the plus minus half MJ functions, which makes it EPR active. So of course there are many ytterbium-3 complexes, but not all of them would be EPR active, because if they're highly axial, so if the ground state is, let's say, the plus minus 7.5, then this will not be EPR active. So the other thing is that this Kramer's doublet has a separation of about 460 wave numbers from the first excited state. This is about 600 Kelvin, so at room temperature, this is thermally isolated. So we have a two-level system which is thermally isolated. This is the first DiVincenzo criterion. So we thought maybe we should have a look if back in 2016, if this is appropriate for the implementation of a qubit. And indeed it was. And of course we did now here you see measurements of T1 by inertial recovery and of the phase memory time TM by Haneko as a function of temperature and magnetic field. So we determined TM, which is the critical parameter for such systems to be considered as qubits. It's about a few hundreds of nanoseconds. And we can see here that at about 15, 20 Kelvin, it's getting limited, the phase memory time by T1, which is the longitudinal relaxation time, as you know it from EPR and from NMR. So here, what you see in this slide is a taxonomy, let's say, of mostly molecular qubits. So there is different systems that have been studied, and our ytterbium trensal was located here in the bottom left corner, which is of course not very good. So we would like to improve this. So for example, here for comparison, chromium 7 nickel from the University of Manchester has a TM of 10 microseconds for a concentration of 100 micromolar, fully deuterated. For the system we studied in the solid state now, but at a dilution of 7% in the diamagnetic host lattice, that would correspond to a fluid solution concentration of 200 millimolar, so much more concentrated than that. We had a shorter phase memory time. So then we thought, okay, let's see what is limiting us, why this is so much shorter. So the rest of the talk is going to be about how we can improve on this. So we saw that T1 limits TM at about 15 Kelvin. So then we went and looked at the effect of the phonons, and actually on the coupling of the phonons to the spin. So this is called the magnetoelastic coupling, and we did this both theoretically and experimentally. So the theoretical bit was done by Nick Chilton, and the experimental measurement of the frequency domain magnetic resonance, which is basically an infrared spectrum in a magnetic field, was done by Josh and our collaborators at the High Magnetic Field Laboratory. So what you can see here basically is that we have some vibrations that they have a magnetic field dependence, and this can be extracted by theory via the magnetoelastic coupling. You end up having here a wave function that has both vibrational and magnetic degrees of freedom. So that was nice, but of course T1 is not TM. So then we were looking what can we do to increase TM. And you can see that here the magnetoelastic coupling occurs via the orbital angular momentum degrees of freedom. So we thought, okay, what happens if we suppress this? So that's why we went to gadolinium, because now gadolinium has a 4f7 electronic configuration. So it has no first order orbital angular momentum, but it has a spin, so of 7.5. So you get a term which is 8s7.5. That is devoid to first order of orbital angular momentum. but still we have the same kind of symmetry, high symmetry, trigonal, and then we basically studied the coherent dynamics of this. So we get a really nice EPR spectra, we model all this, we get the parameters of the system, and then we measure its dynamics at high magnetic fields at 200 gigahertz. And we can see now that under these conditions, TM is now increased to 10 microseconds. So we went from 200, 300 nanoseconds to 10 microseconds. So this is like a 1-2 orders of magnitude increase. And now TM is limited at low temperatures by T1. So is that really the orbital angular momentum that has this effect, or is it just because we're at higher frequencies? So basically, if we compare the results for gadolinium to ytterbium trensal, the one that had a TM of few hundreds of nanoseconds at lower frequencies, so this still has about the same TM, ytterbium trensal, and ytterbium has orbital angular momentum, gadolinium doesn't. So this is an indication that actually it is the orbital angular momentum that produces this effect, since gadolinium is quenched. Okay, so this is nice. And if we see now what we did actually improve the phase memory time of the material. So by going from ytterbium trensal to gadolinium trensal at 1%, now we're up here at 10 microseconds. So what's next? So next is the following. So if we take a gadolinium trensal and we measure squid magnetometry, AC, then we get a relaxation time, which is, you see here, of the order of 10 milliseconds. So this is 3 orders of magnitude higher than 240 gigahertz, which you see here. So the question is, if TM is limited at low temperature by T1 at high frequencies, going back to low frequencies, will TM follow the same increase? So can we actually increase by 3 orders of magnitude TM? So going from 10 microseconds to 10 milliseconds, that would be great, actually. So let's see what happens. So, of course, in the case that it doesn't, and you'll see that actually it doesn't, this is happening because of fluctuations of the environment that induce decoherence. And this can be due to many different kinds of fluctuations. You can have fluctuations of the electronic spins that they surround your qubit, your observed spin. So this could be thus dipolar interactions with electrons, or it could be that the nuclear spin path fluctuates, and this can be done in different ways. And then another mechanism for decoherence is the electromagnetic radiation that we actually use to excite the system, that it can flip other spins in the vicinity also, and also the gradient of your magnetic field, the excitation magnetic field, it's inhomogeneous. So this is also producing decoherence for your system. So there is so many things that they can go wrong that I mean, it's surprising that we can measure anything at the end of the day. So let's say, so we measured the gadolinium trensal now at many different concentrations, because here now we want to probe the effect of the dipolar interactions between electrons. So at high concentrations, electronic spins, they are close to each other, and at low concentrations, they're far away from each other. So here you can see all CPR spectra obtained for 2 different concentrations of gadolinium trensal in the diamagnetic host, which is yttrium trensal, so at 0.5% or 10 minus 3% here. So we extract T1 and TMs, and we can see that for the 0.5%, TM is of the order of 1 to 1 point something microseconds. And when we go to the 10 minus 3 dilution, this number increases and it goes from 5 to the 10, 12 microseconds that we have observed also at high frequencies. So now this frequency, these measurements, they are done at X band, where we expect to have this increase. But I mean, it did increase, but not so much TM. So if we look at the concentration dependence of TM, we can see that at high concentrations, so my pointer doesn't work so well, so it has a bit lag in time. So so at high concentrations, we're down here at few hundreds of nanoseconds, and then as we go from 0.5% to 10 minus 1%, 10 minus 2%, TM increases very fast. So this is the effect of removing the electrons from each other, increasing the distance between them. And at 10 minus 3, it's almost saturated. Of course, it's not really clear here if it's saturated or not fully. But when we get to this 10 minus 3%, we're at concentrations of about 30 micromolar, which means that in order to record the 10 minus 4% point, we reach kind of the detection limit of the instrument, and it becomes impracticable. So we will need very, very large single crystals, which we didn't have for 10 minus 4%, and also to record the data for a week or something. But we have this 10 minus 3% that shows signs of saturation. So we can see that diluting is removing the effect of electron and electron dipolar interactions. So if we do the temperature dependence, we can see now that we have a TM that is limited by T1 now at about 40 Kelvin, and it persists also up to 120 Kelvin. So basically, we have a coherent spin system at 120 Kelvin, which is it's very good. Of course, it would be better to go all the way up to room temperature, but 120 Kelvin, it's quite high temperature. For example, one can consider that superconducting qubits, which are the main support for quantum technologies nowadays, they operate at millikelvin temperature. So this is like 5 orders of magnitude higher temperature than this material. So of course, molecular materials present other challenges, but I mean, with respect to being coherent, they are quite good at that. So now this dilution, what happened? We went now even higher in temperature persistence of the coherent magnetic properties. So now we're situated here in this taxonomy diagram. So there is only a couple of molecular materials and then impurities in solids that they perform better. But can we do better than that? So yes, of course. So, but to do so, we would need to somehow negate the effect of all these fluctuations you see here. So let's say that this is our qubit here. So then there is fluctuations by electronic spins that we saw that we can remove by diluting. So that's what I showed you up to now. But then there is all the nuclear spins of the buff, of the diamagnetic host, and also of the molecule itself. And mainly this is the protons. So now we would like to see if we can do something about that. And do something about that, it means we were gonna use a dynamic refocusing pulse sequence, which is an example of which is a CPMG, so a Karl Pulse Mabum Gill sequence, which refocuses the fluctuations of the environment, of the nuclear spin bar. So, but yeah, before I show you this, I will talk about something else. So there are other fluctuations that can be operated also, like the instantaneous diffusion, for example, which is here. or the direct flip-flops. So instantaneous diffusion, what is it? Is it when you observe a spin and you excite it with an electromagnetic pulse, while the spin is transitioning, maybe a neighbor also is transitioning. And this is induced by the same electromagnetic excitation that induces the transition to the first spin. So, and this fluctuation makes that the local magnetic field changes for the spin you observe. So this changes its resonance frequency. So it's a decoherence source. And direct flip-flops, of course, it's like when two of those spins, they fluctuate simultaneously without a variation of angular momentum. So this is a T2 process. And those, they should be linear to the sinus square of the turning angle, which is here. So basically, what we do is in a Hahn echo sequence, you should have here a pi refocusing pulse. If you do this refocusing pulse of variable turning angle, so you vary theta, then you can probe this term in the equation. And so it should be a straight line with the sinus square of the turning angle. And at 0, it should intersect with the y-axis, and this should be the effect of instantaneous diffusion. So we can see here that those lines are just horizontal lines, so there is no slope. So this part of the equation here is negligible. So basically, I said instantaneous diffusion before, which was wrong. This is instantaneous diffusion is dependent on the turning angle. So this behavior here is the indirect flip-flops. So basically what that graph here shows you is that the main source of decoherence for this system under these conditions of concentration and excitation is the indirect flip-flops of the nuclear spins of the bath. So now we come to the question, can we refocus those? Can we negate their effect? And that we can do, as I said before, by a CPMG. And here you see the results. So if here on the x-axis, you have the number of refocusing pulses in such a CPMG sequence. And you can see that the phase memory time, it's increasing linearly with the number of refocusing pulses. And we reach about 200 microseconds after 120 refocusing pulses. So now we have removed the effect of the proton path fluctuations, and we increase the phase memory time. So where does that take us into the diagram I was showing you before? So that takes us all the way up here. And the question now is, can we achieve this performance by chemically engineering our system? So in other words, can we deuterate and see that the phase memory time will increase accordingly? And can we extend this performance at high temperatures, maybe to reach room temperature? That would be great. So those are things we're working on at the moment. So a last thing is that you can coherently drive your system. So this is a transient mutation experiment. And the time it takes to perform an operation is the frequency of this mutation. So here you can see that we can have pi rotation gates in the time of 10 nanoseconds. And for a phase memory time of 10 microseconds, this is a ratio of Tm to the time it takes to implement this gate of 10 to the third to 10 to the fourth. And this is actually one of the Vincenzo criteria. So which should reach 10 to the fourth, and we are up there. This criterion, it kind of expresses the upper limit for the fidelity of the gates one can implement. So those materials, actually, they could be realistic candidates for implementation of qubits. So with this, I would like to thank my group, and Steve in particular, that found out how to use this fantastic instrument that we got from founding from the Novo Nordisk Foundation a year ago. So within a year, now we know how to run kind of relatively complicated experiments, even for the short time we have the instrument. So the rest of my group for all their hard work, and many of other people for the contributions, their contributions to this project over the years. And thank you for your attention.